Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. Today I'll be discussing a concept regarding volumetric strain and how to analyze the volumetric strain of a rectangular bar when it is subjected to axial load along the length. So coming on to the first concept of this lecture series, the volumetric strain. So when an object, when it is loaded with the external load, then in some direction, so there will be change in the dimension due to the effect of the external load, so that it will result in the creation of a strain in all the direction due to the change in the dimension. So this ratio of change in volume of a body to the original volume is called as volumetric strain. So volumetric strain, it is defined as the ratio of change in volume to the original volume of a body is called as volumetric strain. So if V is the original volume and dV is a change in volume occurred due to deformation, then EV, that is a volumetric strain, is given by EV is equal to dV by V, where dV is the change in volume and V is the original volume. So the next concept is to analyze the volumetric strain of the rectangular bar when it is subjected to axial load along the length. So I have just considered a rectangular bar of length L, width B and depth D, which is subjected to axial load of magnitude equal to P in the direction of its length, which is as shown in the figure. So here, let delta L is change in length, delta B is change in width and delta D is change in the depth. So here final length, so as and when the load is applied along the length, so there will be changes in the dimensions, so that the final length is equal to L plus delta L. So final width is B plus delta B and final depth is equal to D plus delta D. So these are the final length, width and depth of the bar, and whenever if I want to determine the volume of the bar before the application of the loading, it is always equal to L into B into D. The product of LBD gives the original volume of the bar. So in order to determine final volume of the bar, it is the product of final length, width and depth, that is nothing but L plus delta L into B plus delta B plus D plus delta D. So here if I just multiply this, if I just take the product of this and if I just substitute, I need to neglect all the smaller terms so that I will get the equation, the resultant equation as LBD plus BD times of delta L plus LB times of delta D plus LD times of delta B. So this is the overall final volume of the bar after the application of loading. So next is I need to determine the change in volume. So as we know that the volumetric strain is nothing but the ratio of change in volume to original volume. So change in volume here is nothing but the final volume minus the initial volume or original volume. So final volume just we have found out, and original volume is product of LBD. So if I just simplify that, I'll get in terms of BD times of delta L plus LB times of delta D plus LD times of delta B. So this is what the change in volume. So in order to find out the volumetric strain, so that is nothing but change in volume to original volume. So that is delta V by V. So delta V I have found out as the above equation. The original volume V is nothing but the product of LBD. So if I just substitute that, I will get it as delta L by L plus delta D by D plus delta B by B. So which is nothing but EV can also be generalized, it can also be generalized as longitudinal strain plus 2 times of lateral strain. Why? Because so here the load is applied along the length, so that there is increase in the length, so that there is an increase in the dimension along the direction of the load applied, and decrease in the dimension along the perpendicular to the direction of the load applied. So therefore I can generalize it as longitudinal strain plus 2 times that of the lateral strain, wherein delta B by B and delta D by D are the lateral strains. So it is taken as longitudinal strain plus 2 times of lateral strain. So next is as I know that the Poisson's ratio, in my previous lecture series I have discussed regarding the Poisson's ratio. So Poisson's ratio is nothing but the ratio of lateral to longitudinal strain. So as we know that it can also be represented as minus 2 times of mu into longitudinal strain. So lateral strain can be expressed in terms of longitudinal strain as 2 times, that is mu times of longitudinal strain with a negative sign, because the load applied, the external load applied here is tensile in nature, and we can expect the decrease in dimension in the perpendicular to the direction of the load applied. So therefore I have got as a negative value. So EV is equal to longitudinal strain minus 2 times of mu into longitudinal strain. So if I just take the common of the longitudinal strain, it is longitudinal strain into 1 minus 2 mu. So as I know that the longitudinal strain is delta L by L, so multiplied by 1 minus 2 mu. So therefore for a rectangular bar, when it is subjected to axial load of magnitude P along its length, the longitudinal strain, the volumetric strain will be given as longitudinal strain into 1 minus 2 mu, wherein longitudinal strain is delta L by L and mu is the Poisson's ratio of the material. Thank you for watching. Please like, share and subscribe the video. Thank you.